We're going to finish up this series of lectures going over some examples of how we can determine the global timing parameters of given synchronous designs. Here we're looking at a simple example that looks more complex than it really is just due to the poor layout. We can determine the setup, the hold, and the propagation delay of this circuit as follows. The setup is based on the intrinsic setup of the flip-flop plus the maximum delay of our combinational logic network minus the propagation delay of the clock. Now, what this tells us is that we are concerned in terms of setup with the longest possible duration our combinational logic network can occur, and the quickest our clock can arrive. If you think about it, those parameters alone will stress our synchronous circuit the most in terms of setup timing. So let's see if we can get a picture of this. This is basically what that path looks like. The hold time and everything else relatively follows the same philosophy. We look at the minimum of the propagation. We look at the fastest that our network combinational logic can solve or come to a stable known value, and the slowest in which the clock will actually arrive, which means that the longer we actually have to hold out our data, longer our combinational logic will have to be stable past that clock edge. So again, we're looking at the worst case that might cause us the most problems. Let's take a look at a simple example here where we're looking at a simple network of gates, a clock buffer, and actually it's not just a buffer, it's an inverter. And let's figure out how we actually go about determining the hold and the setup. So the hold and the setup timing would be done by taking the longest combinational logic path. Again, we say maximum path. Well, that could be maximum in terms of temperature or maximum in terms of the actual path available to us. If we look at this, the path that takes the most, that hits the most gates before it hits the flip-flop will be this path here. And so what we do is we say, okay, the setup time plus that path, so the inverter, the NAND, minus our clock inverter, or a clock buffer that happens to be an inverter. Because if you remember, our clock in setup timing, the longer the clock is skewed, the more time we have to stabilize. So let's take a look at the hold. The hold example is simple also. The idea here is that we're looking at the fastest the combinational logic can toggle. So what we're doing here is we're saying, okay, well, let's see. Since this is a NAND gate, realistically, we're actually looking for the OR. Whichever one of these is low will cause that to go high. So this could short circuit to a 1 by following this path, the shortest path. And so you'll get a 1 irregardless of the values on this side of the logic cone. So this is our shortest path, and that we can represent by saying the NAND, this NAND represent our minimum combinational logic network, our clock inverter, and then our hold time requirement. So it's going to be the hold minus this network plus our clock inverter. Because remember, if our clock gets shifted out, it takes that much longer. We have to hold the signal out past the clock edge to meet timing. So realistically, we've been looking at simple circuits that are isolated and don't deal with other devices. In all reality, we're going to be dealing with outputs and inputs from other chips. We'll be driving other devices, so we'll have to take into account the wire delay that makes up the connectivity, the clock skew from module to module or chip to chip. So let's take a look at some examples here, and again, with these examples, we need to understand, for example, we don't we need to figure out what is the output timing requirements that this has, so that when we constrain this, we understand what the input relative to this looks like. We need to know how much the wiring is. We need to know what's the maximum and minimum times the clock edges will arrive. And we're going to solve to see what those are here. In this simple example, we're going to say that starting at the clock pin, going to the output, tell me what the pin-to-pin delay is in this design. So what I'm going to do here is I'm going to do a clock to output path. I'm going to analyze this path and add up all the delays in between. So the delays are going to be the buffer of the clock plus the propagation of the flip-flop, or the clock to out, plus the buffer of the output. Each of these is a nanosecond based on our little cheat sheet here, and we find that the total clock to output is 3 nanoseconds. Now, somebody says, okay, what is the input to setup timing? Meaning, from this clock to here, what is the timing it takes? What is the setup requirement of this circuit here? So we're going to say the setup of flip-flop 1, which is here, is going to be called 2 nanoseconds, plus the input, the input buffer, which we're saying is 1 nanosecond for any buffer, minus the clock skew. And so we find out that we add those together, 2 plus 1 minus 1 is equal to 2 nanoseconds. And so one thing I forgot to address in the previous slide, which can be addressed here, is if you have min-max delay parameters here, what's worse? What will cause this number to be larger? Well, let's think about that. In minimum, the circuits will toggle faster, which means our buffer will take less time to solve. It'll be a half nanosecond, 500 picoseconds, or what have you. So, and our clock will be skewed less. So, it kind of works in our favor. We actually would end up with a smaller setup requirement, which means that we could hit a faster clock skew, a faster clock frequency. So that means that we're probably more concerned about max, because as we increase these delays, our setup requirement becomes larger. So what about input to hold? What is the hold requirement of the input part of this circuit? Well, the hold of the flip-flop is 0 nanoseconds. Now we have a buffer of the input, and we have our clock. So what we do is we subtract the hold, we subtract the input from the hold and the clock. So what we're saying is that the hold of the flip-flop is basically positively impacted by the input, but adversely impacted by the clock skew, meaning we have to hold the signal out longer past the clock edge if it takes longer for the clock edge to arrive. So the longer the clock edge arrives, the later this is going to have to arrive to meet the hold requirement. So the problem here is that means if we go faster, what we're going to run into is that this clock edge arrives real soon, and conversely, this signal actually arrives even faster. That means it'll actually not hold out as long past the clock edge, so we'll end up with a hold timing violation. So in this circuit, we're actually concerned about the minimum delay parameters, because if a circuit toggles too fast, it might not actually hold out for the entire hold requirement. So let's look at another example, a more complex example, and let's see how we can improve upon it. So we have a simple 2 flip-flop scenario here with some inputs and outputs, and each of our flip-flops has a setup time of 3 nanoseconds and a hold time of 4 nanoseconds and a clock to Q of 5. So what we're looking at here is a simple scenario where we are going to examine the maximum reg-to-reg path delay. Now remember, that is going to be the path that hits the most gates or takes the longest amount of time to solve. Well, I've picked out the slowest path in this design, and I've highlighted it here. And so as we can see, the reg-to-reg path delay is only going to be this path right here. And so it's going to be the clock to out plus the propagation delay of the OR gate plus the setup requirement of this flip-flop. So our register delay comes out to 16 nanoseconds. Now let's look at the setup time for pin A, because our only input to this design is A. So what we're going to see here is the setup time from pin A to the first flip-flop is going to be the setup time plus the data path all the way through to the flip-flop minus our clock skew, because you remember we subtract clock skew when we're doing setup. So let's break those numbers out. We're going to pass through U7, the buffer, and U3, the OR gate. And we're going to have the propagation delay of the clock taken into account. So 3 plus 8 plus 1 minus 2 gives us a setup time of 10 nanoseconds. Let's look at the hold time now. And the hold time is pretty much the same path. It looks exactly the same. But we're looking at the shortest path now, right? And so there's not much we can do here. There's not much variation. So what's going to happen here, though, is we're basically going to go ahead and look at this. We're going to see that our path is A1. We're going to go through the OR gate. We're going to, here's the difference, we're going to subtract the clock skew, because again it works against us, and we end up actually with a negative 2 nanoseconds hold time. So the question you should be asking yourself is, do we meet timing in this design? The answer is no, and we don't meet timing because of the hold violation. This can be fixed with a buffer. It can be fixed relatively simply. We'll not address that at the moment. So let's go ahead and continue our timing evaluation. Let's look at the clock to out path. The clock to out path is going to take the clock relative to the output going through a flip-flop in our design. So it's going to be, we're going to pass through U8, we're going to take the propagation delay there, include the propagation delay or the clock to Q of the flip-flop, through the propagation delay of the AND gate and the propagation delay of the flip-flop, of the buffer there. So if we add those up, it's going to be 2 plus 5 plus 9 plus 6 is 22 nanoseconds. That means the time it'll take to drive data out of our design relative to the clock is 22 nanoseconds. Let's look at the one final data path, and that's the pin-to-pin combinational delay. So that's going strictly from one input to the output, combinational logic only. Okay. Now, what's going to happen here is we're not going to go through any flip-flops, so we're looking strictly at a combinational logic delay. And that's going to be U7, U5, and U6. So what's going to happen here is we will basically add those together, and we're going to get 16 nanoseconds for a pin-to-pin delay. Now what we need to figure out is, what is the maximum clock frequency we can support with this design? Well, the maximum clock frequency is actually going to look at the longest path in our design. And remember, there's 3 possible paths. There's going to be input to reg. So that'll be there's reg to reg. There's going to be clock to out. There's going to be pin to out. And so what we end up with here is timing of 45.5 megahertz, even though we're not actually meeting hold timing. So the question we ask ourselves is, how do we improve timing? So one easy way to improve timing, and this is just a good design philosophy, is to register all the inputs and outputs of our design. This way we guarantee that whenever the data arrives, it'll be cleanly sampled at the input of our module. This will remove any input delays and any output delays. This gives us an easier time of analysis in the sense that we don't have to guess at what's driving us and then take into account our own input delays. Now let's go ahead and just start the recomputation process. And what we see here is our new path. Our new max register delay is much different. Now if you look here, a register to register delay actually is bigger, 17 nanoseconds, but I bet if you guys were to go ahead and solve for the remaining pen to pen and clock to out, you'd find out that this is actually our new longest path. So this is kind of interesting in the sense that what we've done is we've removed some of the timing, we removed some of the elements from the timing path by simplifying our design by adding flip-flops. Now, again, this is expensive, but this fixes timing violations. And you'll see this probably removes our hold time violation. So with that, I'll let you go through an experiment and see if you can figure out what the new clock frequency is. I believe it's around 50 something megahertz, and I believe our hold time is met. This concludes our example portion of the bonus lecture series.